In this lecture, we will be looking at the issue of residual outliers in multilinear regression. So this is a follow-up to our lecture on leverage. And recall, our context here is we have a multilinear regression. So we have P predictors and one response. And so we have the response having this linear relationship with the P predictors, plus our white noise term. And then we have n observations. So each observation, we have an observation for the predictor vector and then the response variable. And our regression equation can be written as this equation 2 here, where the fitted value for the response is equal to h times the observed value for the response, where h is the hat matrix, and then we define the diagonal entries of that hat matrix A, the HII, as the leverages. And so each observation has its own leverage coming from that hat matrix. And we note that if HII is large, then the predictor variable is an outlier. The predictor observation is an outlier in the ith case. And so if we have HII being more than twice the average of the HII, then it may be a cause for concern because it is an outlier with respect to the rest of the predictor observations. We now have to think about what happens when we look at the response. And so recall that we looked at this case where suppose we have the same scatter plot here and here, and then we have a point that has a high leverage. And so that means here the predictor value, so this is the univariate case, so it's the value on the x-axis, is atypical compared to most of the rest of the points. And we may have this type of case where the point actually appears up here, and it looks like it should be consistent with that linear relationship that we postulate between x and y in our regression. And so this would be a non-residual outlier. And over here, if we have that observation being down here, we see this is a residual outlier. And when we move this point from up here to way down here, the result on our least squares fit for the line is to pull this down, and our line looks something like this. And we see that it really now doesn't capture what looks like a linear relationship with a steeper slope amongst these points here. And so this is a residual outlier. And the way that we want to handle this in terms of detection, because this, we want to detect this. We want to determine if this is happening. Because either this data point is correct, and it really does have this major effect on the regression, and we want to look at it and see if that's appropriate, or it's an error in the data set, in which case this erroneous observation is completely messing this up. And when you think about data sets often are very large. They're too large for you to look at. You may be doing a regression, not in a univariate case, but in a higher dimensional setting where you can't graph the linear regression. So you want these types of tools to pick up on these things. And mistakes in data happen all the time. It's important to recognize that when you're doing often academic exercises in classes, you're given data sets that work out very nicely and are set up well. But real life data has problems, has mistakes. They can come from formatting errors. They can come from data entry errors. They can come from all different types of sources, but they really can wreak havoc on the fitting of a model. And so a technique like using this leverage to detect these is really important. But again, the high leverage of the ith observation in this case just tells us that we're far to the right of the cluster. But we want to be able to discern between this non-outlier and this outlier case in terms of the y value. And the secret for that will come in this distance, the vertical distance between the fitted value and the observed value in the ith case. We see here it's large, and we would call this the ith residual. In this case, that ith residual is small. And so we want to look at that. And so the first thing that we talk about is the raw residual. So the ith raw residual. And we define that as epsilon I hat is yi minus yi hat. So it's the difference between the observed value and the predicted value for the response in the ith case. Now, one catch here is we want to think of epsilon I hat as an estimator for the ith white noise term. So recall, in our regression model, we're adding on this ith noise term. And so that epsilon I hat is an estimator for that term. But one issue is we assume that those epsilon i's are white noise, mean zero, and some variance sigma epsilon squared, but that is unknown. Typically, we do not know this a priori. We are also estimating it. So since we don't know that sigma epsilon, that can make it a little bit trickier to know if one of these raw residuals is large. And one approach we can take is to think about a z-score. So if we have that high leverage point, in this case that is a residual outlier in the way that we're drawing it, we know it pulls our regression line down, and this distance here is our raw residual. But what we can do is calculate the sample variance of those raw residuals. We usually call that s squared, and then use the sample standard deviation s to make a z-score here. And so epsilon I hat minus the theoretical mean for the white noise 0 over s gives us a new type of residual that should have a variance or a standard deviation of approximately 1. Think about when you make a z-score with, say, a normally distributed random variable. You subtract the mean, you divide by the standard deviation, and the result is a standard normal, mean 0, variance 1. Similar idea here, defining the ith standardized residual. So that raw residual in the ith case over that sample standard deviation, which is the sample estimate of the standard deviation of the white noise terms. And with no outliers, this should look like the distribution of the theoretical noise terms. Now we define that as white noise with mean 0 invariance sigma epsilon, but the idea here is we are dividing this by s, and so the result is that we should have a 1 here instead of a sigma epsilon. And so what we can do is convert the raw residuals to the standardized residuals and look at their distribution. Look for outliers. Any outliers that are also high leverage points are going to be concerning as possible high leverage residual outliers. If also, for instance, you had assumed that your original noise terms were normal, mean 0, variance sigma epsilon squared, then here you should see something for your standardized residuals that are standard normal. And then you can use all kinds of different analyses to look at the outliers in your histogram. We also can point out that epsilon I hat itself is a random variable. That random variable has a standard error of s times 1 minus its leverage factor, square root. Well, if this is the standard deviation of this variable, this random variable, we also may want to normalize by this instead. Notice the difference here. For the standardized residual, s is fixed across all of the i's. So we're just scaling all of the raw residuals by 1 over s. In this case, we're looking at each individual noise term and its own standard error. And so we could normalize epsilon I hat by its own standard error, and we get the studentized residual. So the ith studentized residual is defined this way. So the ith raw residual divided by its standard error. And again, s is the same as before. It's the sample estimate of sigma sub epsilon. So this is also useful, and we can do the same thing. We can look at the distribution of all of these residuals, look at outliers, especially if the outliers have high leverage values. Now, we have to think about this a little bit, because this s is common to all of the ith studentized residuals. It's just that sample standard deviation of those raw residuals. So one problem is that an extreme outlier can blow this up. Coming back to our picture, when we put this into the mix, that pulled this down, and all of the distances between these points, these vertical distances between these points and the regression line, increased. This is also quite large. The result is that the presence of this high leverage residual outlier increased the sample standard deviation. It increased s. But one problem there is that in this calculation, that increases our denominator. So it shrinks this ith studentized residual. It also increases the denominator for our standardized residual and shrinks these. The point being that extreme outlier inflates that denominator, which then shrinks this studentized residual, and we might miss it. We might not notice a case where you have an actual residual outlier because that increase in the denominator shrunk this whole expression. So what might we want to do? Well, we can go to this concept of the externally studentized residual. And the key in this case is this s sub minus I. The idea here is it is the sample estimate of sigma sub epsilon, so the sample standard deviation of the raw residuals computed by fitting the model with the ith observation removed. So this is why we have a minus I. It indicates the removal of observation I. So let's think about what will happen in our two scenarios of a high leverage non-residual outlier and a high leverage residual outlier. What will happen here? And also notice that this externally studentized residual is the same formula as what we had in the studentized residual, except we replace that s with the s sub minus I. So first, in our non-residual outlier case, so our non-residual but high leverage outlier, we should say non-residual outlier and high leverage outlier, we have a point that looks something like this. And our regression line looks something like that. Now, if we want to compute this s sub minus I, we remove this orange point and redo the regression. So pretend like that orange point isn't there and redo the regression, and we'll get a new line, maybe something like this. It changes a little bit. The point is, this line has a pretty minimal shift from the removal of this orange point, this non-residual outlier that's also a high leverage outlier. One thing that will happen with that is the residuals, the raw residuals, aren't going to change that much. So S and S sub minus I are going to be pretty similar. So the externally studentized residual is going to be similar to the studentized residual in this case. Whether you have S sub minus I or S here won't make that much of a difference. But what about the other case, where we have a residual outlier that is also a high leverage point? In this case, we had very different outcomes for our regression line. With this point included, our regression line looked something like this. But if we then redo the regression with this residual outlier high leverage point removed, then the line snaps back into this form here that fits this cluster much more appropriately. And we note the sample standard deviation of the residuals will change dramatically. In particular, once we remove this residual outlier, it will shrink, just because these points fit the resulting line much better. So that S sub minus I will be quite a bit smaller than S in this type of case, just because the line is shifting so much. Or in the higher dimensional case, the plane or the hyperplane. And so this corrects for that effect that this outlier has on the whole sample standard deviation of the noise terms. So again, we can compute these, look at their distribution, look for large values in that distribution. We can also use this idea of Cook's distance, which builds off of this externally studentized residual, or the R student. And Cook's distance measures the influence of a high leverage point, or that could be a residual outlier. We want to see what influence it has. And so Cook's distance is defined in the following way. Let yj hat minus I be the jth fitted value using estimates for the regression coefficients with the ith observation deleted. So come back to this previous idea of having this ith observation. Think of it as being a residual outlier and a high leverage point, and we remove it. So we do our regression here, which is a better fit. That's our yj hat minus I. Our yj hats are the fitted values with the ith case included, as usual. And so we have those values in these two regimes here, these two different lines. To compute Cook's distance, we take the difference between those fitted values, square them, and then sum them. And so you can think of taking all of the vertical distances between these lines over these points and squaring them and summing them up. And that gives us Cook's distance in the ith case. And so it's measuring how much the regression model is shifting based on removal of the ith observation. And so again, you can take these Cook's distances, we have I of them, and we can look at their distribution. Look for points with a large Cook's distance. And if you have a point that its removal really affects the model, you'll see a bigger Cook's distance. So in Cook's distance, that large numerator is telling you that the removal of that ith case really changes your beta coefficients. And this is another useful tool to try and pick out those outliers that are really affecting the model. And again, in terms of looking at your data set, these are all tools that you can use to try and detect anomalies, to try and detect problems, to try and detect mistakes in the data. And it gives you a way to do it systemically, keeping in mind that in many applications, your data set is not something that you can look at. It's too big, or it's too high dimensional. And so these are tools to help you try to pick out potential issues in your data, whether they just be outliers that really have large influence on your model. You may want to think about that. You may want to what we call Winsorize or trim your data. In some applications, you might want to remove some outliers. In some, you wouldn't. And if you keep them, you just want to know what their influence is. You want to understand the type of observations that are really affecting your regression model because they're high leverage residual outliers.